Alright, hello everybody. This section we're going to talk about some stuff that you've all seen and done before. So we're going to review what log functions are, see where they come up, and then where you can use some of these properties to help you. So let's start with the definition. If b to the y equals x, so let's say we have a base, an exponent y, and the answer is x, then we can say that log base b of x is also y. In fact, this is an if and only if statement. Not only if we know this, we can write it in terms of logs, but we can go back and forth. So these are the same thing. B to the y equals x, log base b of x equals y. Okay, so now this is called exponential form. This is called logarithmic or log form. It's not too bad or hard to remember. Base b, okay? X goes inside of the log, and then the exponent is what the log equals, okay? So b to the y equals x. That's how I always remember it. B to the y equals x. Now, there are some restrictions. Since these two expressions are interchangeable, and we're talking about exponents and logs together here. In 5.1, we saw that the base has to be positive and can never equal 1. So that has the same restriction when you rewrite it in terms of logs. Okay, with that being said, if this is always a positive number, no matter what this exponent is, this x will never equal 0 or a negative number. So we also know that x has to be greater than 0. And this is helpful for finding the domain. Okay, so now as far as the parts, so let's kind of relook at log base b of x equals y. Okay, this is the base. This is the exponent. Okay, and the fancy word for the number or expression that's inside of the log is argument. Okay, the argument can never be a negative number or can never be 0. So that's how you would find the domain if that presented itself. Okay, so this is the definition for a log. It comes from the exponential format. These two things are exactly the same. They're just two different ways of writing something. Sometimes it's more useful to write it in log form. Other times it's more useful to leave it in exponential, and we'll see when that happens. Okay, so now, some things that you should know. Okay, based on these definitions, logs are exponents. Y is an exponent, whether it's in this format or in this format. And since this equals a log of something, we say that logs are actually just going to be exponents. Okay, so make sure you remember that logs are exponents. And we'll see this more a little later, but logs are also the inverse of exponential functions. Okay? And now a helpful way of reading this, okay? This is how I read this and should help you also evaluate some of these things. A log, so this is kind of like another version of the definition. A log is the exponent. So if we're using the same symbols, a log is the exponent that a base, in this case b, must be raised to in order to get x. Okay? So this is the exponent that b has to be raised to get x. That's a good way to think about it. And that'll help you do some of the things that you need to do in this section. Okay, so here are some examples of converting back and forth. So let's say we have the expression or the equation 4 squared equals 16. Okay, you can write this also in log format. They're the same thing by saying that log base 4 of 16 equals 2. Okay, so again, log base 4 of 16 equals 2. This 4 is a subscript. Make sure that it's clear when you're writing this out. Let's do one the other way. Let's say we have log base 5 of the square root of 5 equals 1/2. Okay, so again, identify the base. The base is 5. The exponent is what the log equals, so that's to the 1/2. 5 to the 1/2 is going to be the same as the square root of 5. Okay, so converting back and forth is pretty easy. And now on your calculators, of course I didn't bring mine with, well, the kind that you guys have, but on my calculator, I have a little ln, okay, which you also have on the calculator. But in addition to that, you also have another button that says log. Okay, so here are some conventions. Oops, let me zoom back up. So, log base 10 of x is frequently written as just log x. So a lot of times we don't need or write the subscript 10. Just like a square root, we usually don't write the little 2, the index with the root, because it's so common. It's the same thing with logs. 10 is such a common base that we assume it's base 10 if it's not written. The other frequent base that we use is base e, Euler's number that we talked about in 5.2. So log base e of x is also the same thing as ln of x. This stands for natural log. Okay, so log base e of x is the same as the natural log of x. Okay, so these two buttons, if you find them on your calculator, are two ways to evaluate logs, specifically in base 10 and in base e. Okay, so we'll only focus on those two bases in this section. We'll learn some more properties and stuff to see what's going to happen if we change bases and we have different things going on. But that's all the background. Okay, so now you have all the background that you need to kind of see the main problems that we're going to see in this section. Okay, so let's just do a few examples. So where do these come up? Here's one example of where you may not remember or even know, maybe, that a log is going to come up. If I give you a function f of x equal to 2x plus 3, let's say I wanted to do several things with that. Let's say I wanted you to graph f of x. Let's say I want you to find the inverse. I want you to graph the inverse. And then let's do domain and range for both. Okay, so let's say we have that example. Now, this is not too bad. Hopefully you remember from previous sections that if you want, you can make a quick little table, but you already know that there's going to be a horizontal asymptote at y equals 3. And if you don't remember what points to use, let's say you plug in -1, 0, and 1. 2 to the minus 1 is 1/2. So 1/2 plus 3. When you're at -1, you're at 3.5. If you're at 0, 2 to the 0 plus 3 is going to be 4. So that means we're going to have a y-intercept of 4. And if you plug in 1, 2 to the 1 is 2, plus 3 is 5. So at 1, we're going to be up at 5. And here is what the graph looks like. Okay, so don't forget we have a horizontal asymptote. The exponential function is going to increase. And now, so there's the graph of f of x. And, let's come back to this in a second. I don't even need to find the inverse to graph the inverse, right? So if I wanted to find the inverse, or graph the inverse rather, we learned a few chapters ago that you can simply switch the coordinates, right? X's and Y's just flip around. So instead of -1, 3.5, I'll make x 3.5 and y -1. Instead of 0, 4, I'll graph 4, 0. And instead of 1, 5, I'll graph 5, 1. So I'll do that graph in blue. So at 1, 2, 3.5, we're at -1. At 4, we're at 0. And at 5, we're at 1. Okay, and it may be kind of hard to just see what the shape is going to be, but here's what we do know, right? If y equals 3 is an asymptote, well, when you flip all the x's and y's, now we get that x equals 3 is an asymptote for the log, or for the inverse. Whoops, spoke too soon. You probably already knew that, but. So then what happens is you get something that looks kind of like that, where it does increase just slower. And there's the graph of the inverse. And if you remember your inverse rules, remember that if you draw the line y equals x, that these should kind of be mirror images of each other. So that's one way to know that you've done things correctly. All right, so there's the inverse graph. Now, so we've done that. Domain and range, we can certainly do that for both. The domain for f of x, horizontal asymptote was at 3. That did not affect the domain, but that did affect the range. So the range is from 3 to infinity. When we do the inverse, remember that if x's and y switch, the domain and range are going to switch. So now the domain is from 3 to infinity, and the range is from -infinity to infinity, and that kind of makes sense. If you have a horizontal at y equals 3, you can't go any lower than 3. When you switch that, now it just means we can't go any more left than x equals 3. Okay, so that's the domain and range for both. Now, as far as finding the inverse, okay, so let's talk about that real quick. I'm going to rewrite this as y equals 2 to the x plus 3. If you forgot how to find inverses, one of the things that we did was just switch the x's and y's. So again, there's that theme, switching x's and y's. Once you switch x and y, you try to get a new rule for y, so you get y alone. So if I subtract 3, I get x minus 3 equals 2 to the y. And then here, we reach a place where we really don't know what to do anymore. Okay, I like to always teach it this way. I kind of get to a certain point in this chapter, and then I usually get stuck. Okay, I can't really get y alone anymore. When you get to this point, this is a perfect time to switch the mode. So currently this is an exponential format. All right, if we switch this to log form, let's do that. So this would be log, the base is 2, the argument is going to be x minus 3, and again the exponent is going to be y. So when we switch the format, all of a sudden now y is alone. Okay, so there's our inverse. Our inverse is going to be log base 2 of x minus 3. And we already have the graph for it. It's right up here in blue. Okay? Just a couple more examples here. Oh, one other thing actually. Now, I said earlier that the argument in here can never be negative, right? So I could later on, instead of graphing and doing all these details, I may just ask you to find the domain. Okay, so without graphing and doing all these things that we did up here, if you just said, if I had, here's this log function, what's the domain? What you can say is that since this argument can never be negative, you set x minus 3 greater than 0. Sorry, it can't be negative and it also cannot be 0, so x minus 3 has to be positive. If you solve, you get x is greater than 3, and that confirms what we had up here in our sketch. Okay, so that's just another way to find the domain. Okay? Another quick example. Let's say I wanted to graph, just a graph, log base 3 of x minus 1 equal to y. Okay, this x minus 1 is not inside the log. If you don't see parentheses, this means only the x's. Alright, now as far as graphing, plugging in numbers into here, it looks kind of weird. Okay, so I'm going to try to actually...
Just a reminder, this is Student of the Month this morning, room 102. If you are in here for Student of the Month, please come on down here, 102.
I'm going to try to actually switch the format. So first I'm going to add 1. And then here's that place again where we're kind of stuck, right? So now if I switch it to exponential, the base is 3, the exponent's y plus 1, that's going to equal x. Here I have an alternate version. So this equation up here is identical to this one. And now maybe it's a little easier to plug numbers into this equation, but plug them in backwards and plug them into y. So maybe if I do negative 2, negative 1, 0, 1, 2, when you plug in these values, 3 to the minus 2 plus 1 is going to be 1/3. If you do 3 to the negative 1 plus 1, that's 3 to the 0, which is 1. 3 to the 0 plus 1 is 3. 3 to the 1 plus 1 is going to be 9. And 3 to the 2 plus 1 is going to be 27. So there's your table, and now you got your graph. Okay, so at 1/3, we're at negative 2. 1, we're at negative 1. 3, we're at 0. All the way at 9, we're at 1. So here it is again. Vertical asymptote at x equals 0, and I know that because if I take the argument, I know that x has to always be positive, so there's our wall, so to speak. Our asymptote will be at x equals 0. Okay? Last skills for this section. Let's say we wanted to solve a couple of equations. So let's say we wanted to solve 2 times 10 to the x minus 3 equals 112. Okay, so let's just go for it. Hopefully your intuition is saying, well, if I'm trying to get x alone, I could undo this multiplication right here and divide by 2. So 10 to the x minus 3 is going to be 56. But now I reach a point where I'm stuck. What do we do when we're stuck? Let's try switching it. So this is log, base is 10, 56 becomes the argument, and then the exponent is what my log equals. And now I have x no longer in the exponent, and I can get x alone. So this is log base 10 of 56. I can add 3 to it, and that's going to equal x. Again, this 3 and 56 are separate. Okay. Another way to write your answer would be plain old log without the base 10, log 56 plus 3. So this is the exact answer. If you wanted to get an approximation, you can type that in the calculator. Let me do that real quick. Mine's a little different, so I'm not even going to show it on mine, but you just press the log button, type in 56, close the parentheses, and add 3. Let's see, I'm getting 56. About 4.75. Okay. The last example. Let's say we have e to the 3x plus 1 equals 51. I'm already stuck, so let's switch it. This is log base e of 51 equals 3x plus 1. You can get x alone now, just subtract 1, and then divide everything by 3. Remember, log base e is the same as natural log of 51 minus 1 over 3, so this is the exact answer. And this is the approximation right here. So if you type this in, just press the natural log button. (51), close the parentheses, subtract 1, divide by, hit enter, and then divide everything by 3. You get about 0.98. Okay, so type it in, take everything divided by 3, you get about 8. Alright guys, that's it for today's lesson. I'll see you guys tomorrow.